linked list allocator uses an ordered list to store information about the allocated and free regions of memory. Regions can be sorted either by the base address or by the size, each approach having its own advantages and disadvantages. Sorting by size is more advantageous for the allocate operation, because we can find a region of the appropriate size more quickly. But keep in mind that this is a linked list, so accessing elements is done in O of n, meaning that it is not possible to optimize search using algorithms like binary search. If we can observe a certain pattern in how allocations are done, for example, small allocations are more frequent than large allocations, we can tune the sorting algorithm to keep these sizes closer to the beginning of the list. Sorting by the base address is more advantageous for the free operation. After freeing a region of memory, we need to access its neighbors to see if we can merge the free regions. Because elements in the linked list are linked to their neighbors, we can perform this merging operation if O of 1. But if we were to sort by size, we would have to search the entire list for the neighbors, which is done in O of n. I decided to sort my elements using the base address, but I'm definitely curious on how a list sorted by size would perform. Now let's talk about the implementation. We will begin the implementation with the linked list region structure, which represents an element in the linked list. The base, size, and type hold the information about the region. We also need pointers to the next and previous elements. The clear and set functions are just convenient ways to set all the fields at once. Next, we will create the linked list allocator class, which is derived from allocator. It has a constructor and overrides the allocate, free, and initialize implementation methods. The first and last fields are pointers to the first and last element of the linked list. Let's see how we can implement these methods. The constructor is fairly straightforward. We simply want to initialize the two fields to null. In the initialize method, we need to insert all the regions into the linked list. We will break this down into 3 steps. First, we need to somehow allocate and fill a new element structure. We will worry about this later. For now, let's just create a new region function that returns a pointer to a structure that we can fill. The second step would be to find the insertion position of this new element. This is what the find insertion position function will do, and we will return a pointer to the element before which we can insert the new element while keeping the list sorted. Finally, the insert region function will insert the element into the linked list. The allocate method simply calls allocate internal, where the actual implementation is. The basic idea of allocating memory is to find a free region that has enough space and break it up into 2 regions, one used and one for the rest of the free space, if there is any. Same as I did with the bitmap allocator, I put the actual search strategy into a function called find free region. As with the bitmap allocator, we can use multiple search strategies here. If no region is found, that means we are out of memory and we will return null. The next step would be to split the region up into 2 parts, but only if the size of the region is greater than the number of blocks we want to allocate. If the sizes are equal, that means that there is no free space remaining in this region, so we simply change the type of the region from free to used. Else, we create a new used region that will be in front of the free region that we found, and then we decrease the size of the free region. Now, let's see the implementation of the find free region function. Starting with the first fit strategy, all we have to do here is iterate through all the elements in the list until we find one that is free and the size is greater or equal to the number of blocks we are trying to allocate. For next fit, we will remember the last region we found in a next field. The search starts from next. When we reach the end of the linked list, we need to wrap around to the beginning, and we will end the search either when we find what we are looking for, or we've reached next again, which means that we've looped through the entire list. For best fit, we are trying to find the smallest free region that can fit the number of blocks. Similarly, for worst fit, we are trying to find the largest free region that can fit the number of blocks. The free operation is a bit more complicated. After marking the current region as free, if any of the neighboring regions are also free, we want to merge these regions together. The first step is to find the region, which of course is something for future us to do. If no region is found, or if the region is not a reserved one, we can bail out. We mark the region as free, and then we need to check the neighbors. Starting with the left neighbor, if that neighbor exists and it is a free region, then we merge these two together. We take its base, occupy its space, steal its wife, take its children, and then erase it from existence. The delete and release region function will be, as you guessed it, a problem for future us. Then we have to do the same with the right neighbor. Now let's take care of the linked list related functions. Find region is used to search for a region that has a specific base address. The implementation is pretty straightforward. We start from the first element and iterate through the elements in the list by navigating from an element to the next. We iterate while the address we are searching for is larger than the current region's base address. Finally, we verify if the base we are searching for is equal to the base of the region, since we are looking for an exact match, and return the region. Find insertion position is very similar to find region, except that it doesn't do the final check. We can in fact modify find region so it calls find insertion position to keep the code cleaner. Insert region inserts an element into the linked list in the position before the insert before element. There are several cases here. If there are no elements in the linked list, the first and last pointers are null. In this case, the inserted element becomes the first and last elements of the list. Since this is the only element in the list, there are no next or previous elements, so these will be null. The second case is when the argument insert before is null. This can happen when the insertion position is at the end of the linked list. In this case, we place the element as the last element on the list. The element that was previously the last element will now link to this new element as its next element. The element that was previously the last element will now link to this new element as its next. The third case is when the insertion position is right at the beginning of the list. We can check for this condition either by comparing the insert before element with the first element or by checking if its previous element is null. In this case, we put the new element at the beginning of the linked list and modify the now second element to link to the first. The final case is when the insertion position is somewhere in the middle of the linked list. In this case, we set up the correct pointers to the next and previous elements and also update the neighbors to point to this new element that we inserted. Delete region deletes an element from the linked list. The basic idea here is that we modify the previous and next pointers of the neighbors to point to the correct elements. If the region is either the first or the last element in the list, we must also update these pointers. Something I'd like to add here is that when we use the next fit search strategy, we could end up deleting the element that was saved. To address this issue, we should make this method virtual and override it in the class implementing the next fit strategy. If the currently saved element is being deleted, we reset the next pointer. The delete and release region method is a convenience method that calls both delete region and release region. It's time to take care of the allocate region and release region functions. What do you do when you need to allocate and free memory, but you are the actual allocator, so there's no one else to help you? You use object pools. So we will use the following strategy. We will create a static pool of linked list region objects, or in other words, an array, allocated at compile time. This will work for a while, but if there are a lot of allocated regions, we may end up with more elements that can fit in our array. To avoid this issue, when the pool usage gets above a certain threshold, we will allocate a block of memory and use it to extend our pool. To keep track of these extended pools that we allocated, we'll link them together, essentially creating a linked list. This is very similar to how the deck container works from the C++ standard library. Let's begin by adding an element used field in the linked list region structure. We will use this to mark whether an element in the pool is free or used. The clear method will set this field to false and the set method will set it to true. Next, we will declare the static pool size constant, which will define how large our initial pool is. We will also need this structure that we will use to keep track of the pools that we have allocated. We have a pointer to the next element in the pool. We won't need to navigate backwards, so a previous pointer is not needed. We also have a size and a pointer to where the array of blocks is stored. I already mentioned the new region and released region functions that we will add, and in addition to these we will also have grow pool. We will also need a few additional fields. The total capacity will give us the total capacity of all the pools together. Used regions will tell us how many regions of the entire pool are used. First pool will be the first pool in the linked list, and it will point to the static region pool array that holds the first couple of elements. The current pool and current pool next free fields will be used to remember where we found the last free block in the pool so that the next searches will be faster. First, we will need to initialize these new fields in the constructor. The initial total capacity is equal to the static pool size. The initial number of used blocks is 0, and the current pool is the first pool. We also want to memset the entire array to 0 to make sure that all the blocks are marked as free. Then we will initialize the fields in the first pool field. We want this to point to the array field. To make things a bit easier, I decided to make this a circular list, so the next pointer points to itself. The next change will be in the allocate function, where we will add a check that when we reach 80% usage, we want to grow the pool of elements. Similarly, we should also be able to shrink the pool in the free function. I decided, however, to leave this as an exercise to the viewer. Time to implement the new region function. This function will iterate through all the regions until it finds one that is free. We ensure that an infinite loop doesn't happen here by making sure that used blocks is smaller than the total capacity. At every iteration, we increment the current pool next free field. When we reach the size of the current pool, we will go to the next pool in the linked list. Eventually, we should be able to find an element in the pool that is unused. When we find one, we increase the number of used blocks and return that element that we found. The released region function is pretty simple. It just clears the element and decrements the number of used blocks. Finally, we have the grow pool function. Here, we call the allocate internal function to allocate a block for us to use. Since we are calling this function when we reach 80% capacity, we should still have a couple of free elements to use, so this allocation should work just fine. We will divide this block into two sections. The first will hold a linked list block pool object, which will act as a header, and the rest of the block will contain an array of as many linked list regions as it can fit. The blocks field in the header will point to where this array begins, which would be the address of the block plus the size of the header structure. Finally, we insert this pool into the linked list by placing it right after the first pool and increase the capacity. Where we actually place the block doesn't matter. We really don't care about the order that these pools are in the list. All we care about is extending the capacity. Now that we finished the implementation, let's discuss about the additional operations that we might want to do with an allocator. Checking the state of an address is pretty straightforward. You can simply call the find insertion position function to find a region where that address that you're searching for should be in. This will have a memory complexity of O of n. Not as efficient as the bitmap allocator, where this can be done in O of 1. Storing metadata about allocated memory regions is trivial with this allocator. All you have to do is add whatever information you want to this linked list region structure. Next, Let's look at the performance analysis of this allocator. Remember that the allocate operation performs a search to find a free region, and then splits that region into a used part and a free part. The complexity of the find free region method depends on the search strategy used. The same things we talked about in the bitmap allocator also apply here. In all strategies, we are iterating the list of regions once. However, for first and next fit, we exit as soon as we find an element that's good. And for the best and worst fit, we always go through the entire list. All the strategies have an average complexity of O of n and the worst case complexity of O of n. The difference between them is in the best case, with the first and the next fit having O of 1, but best and worst having O of n. The part where we split the region doesn't really have any kind of loops, so it is done in constant time. Something I'd like to note here is that in this case, n has a slightly different meaning. In the bitmap allocator, n was the size of memory in blocks. Here, n is the number of regions. Well, this gives an advantage to the linked list allocator. In the bitmap allocator, we are always iterating over the bitmap from left to right over a small portion of memory, which means that the CPU's cache will work to our advantage. In the linked list allocator, the blocks may be spread out pretty randomly in memory, and they are also larger in size, which means that we will likely encounter cache misses. We will see some benchmarks later. Until then, let's talk about wasted memory. Unlike the bitmap allocator, the linked list allocator is much less predictable in how it uses memory. Allocating a lot of small regions means that it will require a lot of these structures, which are quite large in comparison to the bitmap allocator, where we only use 1 bit per block. Memory usage will depend a lot on how that memory is being allocated. Many small regions favor the bitmap allocator, while large contiguous region will favor the linked list allocator. In terms of fragmentation, the linked list allocator should perform identically to the bitmap allocator, since it allocates memory in a very similar pattern, with the main difference being on how that memory is being tracked. We will look later at benchmarks. So, while the linked list allocator is a bit more technically difficult to implement than the bitmap allocator, it has a very good performance, but since it is a bit more difficult to implement and its memory usage is not very predictable, I would rather use the bitmap allocator as a physical memory manager. But all in all, it still performs really well, as you will see later. Next, the body allocator. The body allocator uses a structure similar to a binary tree to divide memory. To better understand how this works, let's start with an example. Let's say that we have 64 kilobytes of memory, and to keep things simple, we will assume that it is entirely free. We begin by choosing a block size, which will be the size of the smallest block that can be allocated. We will use 4 kilobyte blocks, just like we did in all the other examples. Next, we divide the memory into blocks, in the same manner that we did with the bitmap allocator. Now, we organize a party, which will result in every 2 blocks becoming bodies. Every pair can now combine to form larger 8 kilobyte blocks. We repeat this process, throw more parties, and every time we get larger and larger blocks. 16 kilobytes, 32 kilobytes, 64 kilobytes. We can either stop at a fixed number of these layers or when we don't have enough memory to form larger blocks. To clarify the terminology that I will use, I numbered layers starting from the largest blocks to the smallest blocks. In other words, layer 0 has the biggest block size and layer n-1 has the smallest block size. Other sources like Wikipedia use a different term, the order, which refers to the power of 2 that you need to multiply the smallest block size with. So the order 0 would mean the smallest block size, while the order n-1 would mean the largest block size. To calculate the block size for a particular layer, we multiply the smallest block size by 2 to the power of the order. If we are using layers, that would be 2 to the power of n-1 minus layer. In our example, we decided on the memory size of 64 kilobytes. So the highest order would be 4, since 4 kilobytes multiplied by 2 to the power of 4 equals 64 kilobytes. So we have a total of 5 layers. Initially, our memory is completely free, so our tree consists of a single unused block of the highest order. Let's say that we want to allocate 10 kilobytes of memory. The closest size of a block we can allocate is 16 kilobytes, which would correspond to a block on layer 2. Looking at our structure, we don't really have any blocks available on layer 2, so we try to find a block on the layer above. We don't have anything on layer 1 either, so we reach level 0, where we find this large 64 kilobyte block. Since this block is much larger than what we want to allocate, we will divide it into 2. Now we have two 32 kilobyte blocks. This is still too large, so we take the first block and divide it again. 16 kilobytes is as low as we can go for 10 kilobytes to fit, so we allocate the first of the 16 kilobyte blocks. Let's try to allocate 4 kilobytes. This corresponds to the size of the smallest blocks on layer 4. Looking at the diagram, there is no free block on layer 4, so we continue our search on layer 3. We don't find any free blocks here either, but we can find this 16 kilobyte block on layer 2. Same as we did before, we divide this block repeatedly until we get a 4 kilobyte block that we can allocate. Let's do one more allocation of an 8 kilobyte block. This corresponds to layer 3. Looking at the diagram, there is a free block on layer 3, so we allocate it. But what's that? We no longer need this 4 kilobyte piece of memory, so we want to free it. The procedure is, we first mark the block as free and then we try to merge it back into a larger block. The body of this 4 kilobyte block is also free, so we can merge the two blocks into one 8 kilobyte block. Unfortunately, the body of this 8 kilobyte block is occupied, so we cannot merge it any further. Oh, we no longer need these 10 kilobytes of memory. Again, we mark the region as free and then see if we can merge it with its body. Its body is divided, so we cannot perform the merge. Now we no longer need this 8 kilobytes of memory. After marking it as free, we look at its body and see that it is also free. So we can merge them into a 16 kilobyte block. The body of the 16 kilobyte block is also free, so we merge again, getting a 32 kilobyte block. The body of this 32 kilobyte block is also free, so we merge them again, obtaining the original 64 kilobyte block. Now that we have a basic idea on how the algorithm works, let's see how we can actually implement it. There are multiple ways in which we could approach this allocator. There are two general ways in which we can represent binary trees into memory, using a linked structure, similar to a linked list, or using an array. In my implementation, I decided to use a bit array. To get a better understanding on how this works, we will redo the example we did, but this time with a focus on the implementation. Our array will look something like this. Note that even though in the diagram the blocks have different widths to make it easier to associate the blocks with their parents, in memory they are all using 1 bit. You may ask, how can we store 3 states that the blocks can be in, free, used, or divided, using only 1 bit? The trick is that we only need to store whether a block is free or not free. We can infer whether that block is used or divided based on the context. First, let's try to allocate 10 kilobytes. The closest block size is 16 kilobytes, which corresponds to layer 2. An interesting observation we can make is that in any layer other than layer 0, if two bodies are both free, they get merged. As a result, on any layer other than layer 0, a free block will always be accompanied by a body that is either used or divided. This is how we can actually perform the search for free blocks on a specific layer. We are going to search for pairs of blocks where one is either divided or used, so a 1, and the other is not. Basically, we are searching for pairs of blocks marked 1, 0 or 0, 1. Since we cannot find any, we will go to layer 1. We can't find any such pair here either, so we look at layer 0. Here the strategy changes. We are searching for a 0, which means that the block is free. We pick the only block that is available and now we have to divide it, so we mark it as a 1. We split the 32 kilobyte block again, so we again mark it with a 1. We pick the first block to allocate, so we mark it as 1. Now I could leave this as it is. We can infer that this is a used block because its two children are 0. But in my implementation I decided to mark all the blocks below as 1, so that the last layer will contain an accurate picture of the entire memory. However, this probably cost me a bit of performance. Let's now allocate 4 kilobytes of memory. This corresponds to layer 4. Using the strategy from before, we cannot find any pair of bodies marked 10 or 01, so we continue the search on layer 3. Same result, we go to layer 2, where we can find these two bodies marked 1 and 0, which is exactly what we're looking for. We pick the block that is free, and then we have to divide it. 8 kilobytes is still larger than the size we want, so we divide again. And we finally allocate the first 4 kilobyte block. Now let's allocate 8 kilobytes of memory. This corresponds to layer 3, where we can find this pair of bodies marked 10. We allocate the free 8 kilobyte block and optionally fill all the blocks below it with a 1. Now let's see how the free operation works. Let's try to free the 4 kilobyte block. We start by marking the block as free, and then we need to check whether we can merge it with its body. The body is free, which means that we can undivide this 8 kilobyte block, so we mark it with a 0. Now we check if the 8 kilobyte block can be merged with its body, but its body is used, so we cannot. Essentially what we are doing here is a bitwise OR operation between each pair of bodies, and we set the state of the parent to the result of this operation. Let's free the 16 kilobyte block. We begin by marking it as 0 again. Its body is divided, and 0 or 1 equals 1, so the state of the 32-bit block remains 1. Finally, we free the 8 kilobyte block. We mark it as 0. Its body is also 0, and 0 or 0 equals 0. So the 16 kilobyte block now has the state 0. Again, the body of this block is 0, 0 or 0 equals 0, so the 32 kilobyte block is also 0. We do this again, and now the 64 kilobyte block is marked as 0, so the entire memory is now free. Now that we understand how the allocator works and how we can implement it, let's actually start looking at the implementation. This is the body allocator class. It looks very similar to all the other allocators. We will have a bunch of fields, the bitmap itself and its allocated size in bytes, the smallest and biggest block size, and the number of blocks on layer 0. Bitmap unit is a constant that contains the size of an element of the bitmap measured in bits. We are using a byte array, so this will be equal to 8. If we were using uint32, this would be equal to 32. Before going any further, let's implement some helper methods to make working with this complicated structure a bit more easily. First, we would like to know how many blocks are on a particular layer. The most obvious response would be to use the memory size divided by the block size for that particular layer. But this could cause problems because the memory size is not always a power of 2. This would cause some blocks to not have 2 children but only 1. This could break some of our calculations. To avoid this problem, only layer 0, which has the biggest blocks, will be calculated based on memory size. The rest will be calculated based on the number of blocks on layer 0. Even if we have some extra blocks that would theoretically fall outside of memory, we can simply mark them as reserved, so they are never used. So, we know how many blocks are on layer 0, and we are doubling the number of blocks on each layer. That means that the number of blocks is 2 to the power of the layer multiplied by the number of blocks on layer 0. The next question is, how can we calculate the index in the array where the layer starts? If we ignore the fact that this is stored in a byte array, we can calculate the index of the bit by adding up all the sizes of the previous layers. If we do the math, we will end up with this expression. The size of block 0 multiplied by 2 to the power of 0 plus 2 to the power of 1 plus etc. plus 2 to the power of layer minus 1. We know from math that the sum of the powers of 2 is equal to 2 to the power of layer, everything minus 1. While it wasn't absolutely necessary, I thought it would be much easier if every layer would begin at bit 0 of a byte. This means that we have to introduce a bit of padding, depending on how many bits we need for each layer to fill up the last byte. This is pretty difficult to calculate without having to iterate through every layer, which we will prefer to avoid. What we can do is to calculate a loose approximation. The important part is that we don't get any overlapping layers, so to be safe, this approximation should give a slightly larger number. What we could do would be to divide the number of blocks on layer 0 by 8, rounding up, and then multiplying by 2 to the power of layer minus 1. Now let's create some helper methods to get or set bits from this data structure. Both of them are very similar to the get and set functions from the bitmap allocator, and we are using the index of layer function to determine where the layer begins. Let's continue with the initialization method. This procedure is almost identical to the bitmap allocator, but with some small differences. I decided to hardcode the number of layers to 10. I can't really justify why I picked this number, but it was a nice and round number that seemed like a good choice. If the smallest block size is 4 kilobytes, the biggest block size would be 2 megabytes in size. Next, I did some calculations to fill the fields of this class, including the biggest block size, the number of blocks on layer 0, and the total size of the bitmap, which can be calculated by getting the index of the layer after the last. After doing these calculations, I searched for a free region where to store this array. Next, I initialized it by marking everything as used, and then I marked the regions starting with the free ones and then the used ones. Finally, I marked the regions used for storing the bitmap structure itself. Let's take a look at these mark region and mark block functions. Just like we did in the bitmap allocator, mark region is meant to be used with regions measured in bytes instead of blocks and simply calls mark blocks after doing the conversions. Mark blocks start by marking everything on the last layer where we have the smallest blocks, same as we did with the bitmap allocator. After that, we bubble the changes up. As I mentioned earlier, this is essentially doing an OR operation between pairs of bodies. What about setBulk? This function sets a range of bits to a specific value. Here I use the same optimization that I had in the bitmap allocator. Instead of setting bits one by one, I use memset for setting whole bytes, which is highly optimized and will result in a much better performance. So, I set bits one by one until the bit index, which is represented by the base variable, becomes a multiple of 8. Then I use memset to set the whole bytes, and finally I set the remaining bits bit by bit. We finally reach the allocate function. The first step would be to calculate the order or layer on which the requested number of blocks should be. This can be done by performing a base 2 logarithm of the number of blocks, which gives us the power to which we have to raise 2 to obtain the number of blocks. Log2 is a helper function I have created, which works by counting the number of leading 0 bits. This is a built-in function in GCC that will most likely be translated to the CLZ assembly instruction. Unfortunately, this function is not perfect because it truncates the result. We would like to round the result up and not down. For example, we want to round a 33 kilobyte block to 64 and not 32. To work around this, I added this check. If the number of blocks is not a power of 2, we add 1 to the result. This would give us the correct order. If we want to know the layer, we just have to invert the result by subtracting the order from the number of layers minus 1. For determining whether a number is a power of 2 or not, we can use this bit twiddling hack by doing a bitwise AND between the number and then number minus 1. On the Wikipedia page for the body allocator, it is mentioned that the allocator cannot allocate blocks any larger than its largest block size. However, I still wanted this allocator to work properly in this case, so here I handle it. If the requested memory is larger than the largest block size that we support, we fall back to using the same algorithm that we used in the bitmap allocator, by searching for undivided blocks on layer 0. While this is not ideal, it is better than not being able to allocate at all. In the normal case, there are a couple of steps that we need to take for the allocation. First, we will search for a free block by searching for a pair of 10 or 01 blocks, as I explained earlier. This is implemented in the findFreeBlock function. Here we have two nested for loops. In the outer loop, we are iterating over each layer, starting with the layer that we calculated earlier and stopping before we reach level 0. In this inner loop, we are iterating over the blocks inside each layer, trying to find the 01 or 10 bit patterns. We could iterate over each block and compare it with its body, but that wouldn't be very efficient. We can do better by iterating over whole bytes. Now, how can we compare multiple bits at the same time? Using bit operations, of course. We are interested in a bit operation that can tell us whether two bits are equal or not. Thinking about it, this is exactly what the exclusive OR operation does. XORing two bits that are equal will result in 0, and XORing two bits that are different will result in 1. What's left to do is separate the bodies, which can be done by applying an alternating bit mask. That's exactly what the AA and 55 constants are, and then shifting one of the numbers so that the bits overlap. If the result of this exclusive OR operation is non-zero, that means that we have found a pair of 01 or 10 bits. To determine exactly which bits are 01 or 10, we can do a base 2 logarithm on the result, which gives us the power to which we have to raise 2 to get this number, which is the same as the index of the bit. The findFreeBlock function needs to return the position of the free block, so what's left to do is figure out which of the bodies is the free block. If it is the first, we return the index, otherwise we return index plus 1. If we didn't find anything so far and we've reached layer 0, we just try to find a free or undivided block on layer 0. Back to the allocate method. Once we find a block, we need to check if it is on the same layer from which we started our search. If it is not, this for loop will go through each layer, dividing the blocks in the process. Since I decided to mark all the blocks below the allocated block with 1s, this is what this next section does. It goes through each of the layers below, filling blocks with 1s. Finally, we mark the block we want to return as used, and then return a pointer to the block. Free is a lot easier to implement. All you have to do here is call the markBlocks function. Something we must be careful with is to mark the exact same number of blocks that we reserved during allocation, which is why we have to round the number of blocks to the nearest power of 2. In the allocation function, when the number of blocks was larger than the biggest block size that we support, we fell back to allocating using the bitmap allocator algorithm, and we only marked the requested number of blocks, not the size of the big blocks. So, in the free function, we don't have to round the number of blocks to a power of 2 in this particular case. That was a lot of work. Now let's take a look at how we can implement the additional operations. Checking the state of an address. Using my array-based implementation, checking whether memory region is free or used works identically to the bitmap allocator. All you have to do is check if the block on the last layer is free or used. This operation can be done in constant time. If I didn't mark all the blocks below a used block with 1s, I would have to walk the tree to figure out whether that address is part of a used or a free block. Storing metadata. Storing metadata about allocated regions presents the same challenges as the bitmap allocator. Every additional bit added to the bitmap structure will double the amount of space used by the allocator. An implementation based on a linked structure will make storing metadata a lot easier. Now, let's look at the performance, starting with the allocate operation. Evaluating the complexity of the allocate operation is slightly more difficult, so let's look at the code and see what loops we have. The findFreeBlock function has two nested loops, one that iterates over the layers and one that iterates over the blocks. The complexity of this function would be O of n times L, where L is the number of layers and n is the memory size. If the number of layers is calculated based on memory size, then the complexity will most likely be O of n log base 2 of n. In any case, L is gonna be smaller or equal to logarithm of n. Going back to the allocate function, we also have this for loop, where we mark the blocks as divided, which depends on the number of layers. So its complexity would be O of L or O of logarithm of n. Next we have this for loop, where we bubble the changes down. Because of the nested loop, this is also O of n times L or O of n times base 2 logarithm of n. Combining all of these together, we would get O of n times L plus n times L. Because in big O notation we only care about the highest order of the polynomial expression, we can remove this L here. We can also eliminate the constant 2, so we're left with the complexity O of n times L or O of n times base 2 logarithm of n. In the free operation, we are calling the markBlocks function, which has the same complexity of O of n times L or O of n times base 2 logarithm of n. Wasted memory. In terms of wasted memory, the body allocator performs slightly worse than the bitmap allocator. It uses double the amount of space for its internal data structures, and it also rounds the number of desired blocks to a power of 2. This means that in many cases more memory will be allocated than necessary. Fragmentation. Fragmentation is pretty difficult to estimate, so I think it would be best to just look at the data. We will do that a bit later. So, to put it briefly, the body allocator is a bit more technically challenging to implement than the bitmap or the linked list allocators. For managing physical pages, it's not that great, but as we will see later, it's a great allocator for managing the heap. While the allocators that I've talked about so far are the most commonly used and talked about, memory allocation is an area where a lot of experimentation can be done. More advanced operating systems might employ a combination of these techniques or different techniques altogether. A good approach to doing these types of experiments would be to observe real-life memory usage patterns and, based on these usage patterns, to think of and design an allocator that can maximize the desired performance characteristics. I did some experimentation of my own, so here I will present 2 or maybe 3 alternative allocators. In my first experiment, I wanted to change the linked list allocator to use a binary search tree instead of a linked list. A binary search tree is essentially a binary tree where, given any node, the subtree on the left side will only contain elements smaller than the current node, and the subtree on the right will only contain the elements larger. Explaining how the binary search tree algorithm works is beyond the scope of this video, so I will put a link in the description if you want to know more. The important part is that using this algorithm we can improve search from O of n to O of log base 2 of n when searching for whatever thing we decide to sort by, which is a significant improvement. Now the question is, what should we sort by? We have 2 options. We can sort by the base address or by the size. The only place where we search by the base address is in the free operation, thus sorting by the base address will improve the speed of the free operation. In the allocate operation we search by size, so sorting by size will improve the speed of the allocate operation. In my implementation, I decided to sort by the base address. Let's take a quick look at the implementation. Most of it is very similar to the linked list allocator, so I will only highlight the things that are different. The structure of an element looks a bit different. We have pointers that point to the parent node, to the node on the left and the right. Obviously, another difference will be in the implementation of insert region and delete region, which will now work slightly different. But since I decided not to discuss how the binary search tree works, I will skip on the explanation for these 2 methods. Now let's talk about findFreeRegion, which is called during allocation. The order in which we search for free regions isn't that important. So what I have implemented here is a depth-first search through the tree. I first go recursively to the left side and then to the right side. In the free operation, here is where I am searching by the base address. After finding the region and then marking it as free, we need to check the neighboring regions and see if we can merge them. The get predecessor and get successor methods are basically operations specific to binary search trees that can help us navigate elements in their sorting order. You can check the link in the description for a better explanation about how binary search trees work and how their operations can be implemented. A common issue with binary search trees is that they can end up unbalanced. And here is an example of this happening. Both of these trees are valid binary search trees, but the tree on the right is much deeper and has a lot of empty slots. When this happens, we lose a lot of efficiency when searching. There are various techniques that can be used to maintain a balanced tree. For example, AVL trees or red-black trees. But because these were pretty difficult to implement and I just wanted to try this as a proof of concept, I decided to simply use the std map container from the standard library, which does use a balanced binary tree in its implementation, typically a red-black tree. Obviously, this allocator would be pretty difficult to port in an actual operating system where we don't have the standard template library. And here's the implementation. The structure of a region is really simple. We only have base, size, and type. And this is the magic map that makes everything happen. It does all the hard work for us. Let's go to the allocate method. Here I iterate over all the regions in the map until I find one that is free and large enough for what we're looking for. If needed, we split the region into a used or reserved and a free region. And this is the free method. Here I use the find operation to find the region. This find operation will return an iterator, and then we can use this iterator to navigate to the predecessor, which I do here, and to the successor, which I do here. And the rest is pretty much the same. While thinking about how to improve these allocators, I realized that during allocation we are wasting a lot of time iterating over used blocks. So I thought, why not put the free and the used regions in separate binary search trees? This way I can also use different sorting orders. For allocations, we are searching for a region that has a specific size, so we can order the free regions by size. And for freeing, we are searching for a region based on the base address, so we can order the used regions by the address. And this is my implementation of this idea, the dual balance binary search tree allocator. Again, I used the map from the standard library, but this time we have two different maps. Since we can have multiple regions with the same size, we will use the multi-map container for the free region map. And this is the reserved map. During allocation, we search the free region map for regions that have at least the number of blocks we are looking for. I noticed here a bit too late that I could have made this more efficient by using the lower bound operation of the map, which returns an iterator to the first element that's larger or equal to the number that we are searching for. That would have been much faster than iterating through the list like I did here. Unfortunately, I found this problem after I already edited almost the entire video, but I might make a follow-up video regarding the benchmarks if I find any significant differences in the results. Once I find the region, I remove it from the free map and move it to the reserved map. And if the region is larger than the number of requested blocks, then we will split it and put the remainder in the free map. In the free implementation, after finding the region, I remove it from the reserved map and then place it back into the free map. Unfortunately, here we still need to do an inefficient lookup by address. We need to find the predecessor and then the successor of the region we just added. Because we need to search by the base address, we cannot take advantage of the more efficient find operation. We have to iterate through the entire map. It's it's finally time to talk about the benchmarks. We want to know which algorithm is the fastest, which one has the least fragmentation, and also which one wastes the least amount of memory. But the big issue is that to get a proper benchmark, we need to design a good test. A bad testing methodology will not only result in us thinking that a particular algorithm is better or worse, but we might end up choosing an algorithm that will perform poorly in our operating system, even though the benchmark said it was the best. Another caveat I'd like to mention is that these benchmarks that I will present are benchmarks of my code. It is very likely that I missed some optimizations that could completely change the results. Someone else's implementation might perform differently. Also, in many cases, I had to make choices in how I implemented a particular algorithm. Maybe the choice I made wasn't the best, and using an alternative approach would have gotten a much better performance in a certain category. This is why I think it's useful to just try it out. Implement more than one approach and compare them. This is ultimately the reason why I made this whole video. I could have just made a video about the bitmap allocator, but I wanted to be able to compare, and I ended up implementing all these algorithms. And even after doing all of this, I still have ideas that I'd like to try out, but ultimately decided not to because of the limited time. Now, let's think about how these allocation functions will be called, and let's try to identify what are the main variables that can change how an implementation behaves. The most obvious one is how big the memory is. In the bitmap allocator, searching for free blocks will depend on how large the memory is, but in the linked list allocator, searching depends on how many regions are stored in the linked list, a completely different approach. The next variable is how full the memory is. If the memory is fuller, the allocators might find it more difficult to find a free region. The third variable would be the region size requested by the user during allocation or deallocation. Finding a large region of free memory will probably take longer than finding a small region. The question here is, how frequently does the user request smaller regions as opposed to larger regions? Unfortunately, I wasn't able to find much information about this topic or research, and testing existing software is pretty difficult, so I just made an informed decision. I could be wrong, and if you find any data supporting this, please let me know and I will retest everything with the new data. But what makes the most sense to me is that the allocations of small regions are more frequent than the ones with large regions, and they follow an exponential distribution. So in my tests, I used a random number generator with the geometric distribution, which is the integer equivalent of the exponential distribution. If you take a large number of random samples with this distribution and count how many times you get each number, you will get a plot that looks similar to this. Something in particular about our physical allocator scenario is that this allocator will mainly be used by the virtual memory manager, which only requests single blocks that it can map to virtual addresses. Drivers might require to allocate larger regions, but predominantly we will need to allocate regions consisting of single blocks. So the fourth variable I introduced was the percentage of these size 1 blocks. Now, let's begin testing the speed, and we'll start with a baseline test. Let's take the average for each variable, and then we will analyze how the performance of each algorithm changes based on each of these variables. I started with a memory size of 128 megabytes, a memory usage of 50%, and the percentage of size 1 blocks at 50%. And these are the first results. The bitmap allocator with the first fit got a pretty good result, being in third place with a 64 microsecond on average. The next fit optimization does have a significant impact on performance, giving us an 80% average speed improvement. And this makes a lot of sense. We're starting our search in the area that is most likely to contain free regions, rather than searching from the beginning every time. However, we are getting a lot less consistent times between tests. The best and worst fit, as expected, perform terribly, since they have to iterate over the entire memory every time. The worst fit has a significantly worse performance, which is something I find a bit odd, given that the only difference between the two implementations is just a comparison operator. Perhaps there are some compiler optimizations I may not be aware of. Moving forward to the linked list, the first fit implementation had a significantly worse performance than the first fit bitmap allocator. This can probably be explained by the fact that we have a large number of small regions, since we set the percentage of size 1 blocks at 50%. Small regions are more costly for the linked list allocator than the bitmap allocator. But using the next fit optimization, we can see that the linked list allocator beats the bitmap allocator and is the best performing allocator of all. The best fit and worst fit of the linked list also perform pretty badly. Oddly enough, here the best fit and worst fit perform within margin of error of each other. The body allocator got a pretty average result, which is pretty much what we expected, being between the bitmap allocator first fit and the linked list allocator first fit. The plain binary search tree allocator didn't do that great. The binary search tree seems to do more harm than good, giving us a second to last performance. Using the better optimized and also balanced binary tree implementation from the standard library, we shaved off a few nanoseconds, putting us within margin of error of the linked list best fit implementation. The biggest surprise for me was the implementation that used separate binary search tree for free and used regions, which performed really well, being on the third place. It might be worth trying some more experiments with this allocator, such as combining this with the linked list next fit allocator. Perhaps we could get an even better result. But what about the performance of the free method? Here we see a lot less variation between the different implementations. Both the linked list and bitmap allocators have a very similar performance. You could say that they are within margin of error. We shouldn't expect any difference between the different variants like first fit or next fit, since these strategies only apply to allocation. The implementation of free should be identical. The body allocator performs only slightly worse, which can be explained by the fact that it has to update bits in multiple layers. The balanced binary tree probably needs to do some tree rebalancing when regions are deleted or changed, giving it a slight performance penalty. In the dual binary search tree implementation, these changes are compounded since a free operation means deleting from the free tree and inserting that region back into the used tree. Now that we've established a baseline, let's analyze the variables and see how they affect performance. And let's start with the memory size. This chart looks a bit messy, so let's switch to a logarithmic scale. This is much better. Starting with the best performing algorithms, here we can see that the linked list next fit, bitmap next fit, and dual binary search tree implementations aren't affected at all by having a larger memory size. This makes them great candidates for managing a large amount of memory. The bitmap allocator first fit is only slightly affected by a bigger memory space, with the 1 GB memory only taking double the amount of time of the 32 MB. The rest of the algorithms, though, are significantly affected by memory size. Looking at this chart for the free operations, the times are mostly constant for all the algorithms and don't seem to be affected by memory size. Let's look at the next variable, the percentage of memory used. Here we can also learn some interesting things. Again, the best performing algorithms, linked list next fit, bitmap allocator next fit, and the dual binary search tree don't seem to be affected by how full the memory is. The bitmap first fit is only slightly affected, which makes sense. When memory is fuller, the first free region might be further away from the beginning of the bitmap. An interesting outlier is the body allocator, where between 50 and 75% memory usage, the performance actually improves. This has a good explanation, because the more memory gets filled up, blocks on higher levels are marked to used, meaning that we spend less time searching. All the bitmap allocators, regardless of strategy, aren't much affected by how full memory is. However, all the linked list allocators are severely affected. This makes sense. More memory fill means that the linked lists will have a larger number of elements, and searching through them will take more time. The binary search tree implementation have a similar problem, since searching for regions is still done in O of n. What about the ratio of one block allocations? Again, we see that the best performing algorithms, the bitmap allocator next fit, The linked list next fit and the double binary search tree algorithms don't seem to be impacted at all by how many small blocks we allocate. The body allocator does something really interesting. It performs really well when we just use the exponential distribution, but at 25%, 50%, and 75% allocations of one block, the performance gets worse. What is really interesting is that when we get to 100% allocations of just one block, the performance seems to improve, which is contrary to what I expected. Another interesting trend that we can see is that the average performance of the bitmap allocators improves when we're searching for fewer blocks. This is somewhat expected. Finding a smaller region is easier than a larger region and should be faster. The opposite happens with all the linked list allocators. This makes a lot of sense. Having a lot of small regions means that the number of linked elements is a lot larger, meaning that searching will take longer. The binary search tree implementations also exhibit the same behavior. Let's also take a look at the free operation. Here we can see a similar trend, although much less pronounced. The bitmap allocators tend to be faster when we have a lot of smaller regions, while the linked lists tend to stay the same or be slightly worse. What have we learned so far by looking at these performance graphs? The main takeaway is that using either the bitmap allocator next fit, the linked list next fit, and the dual binary search tree algorithm is a great idea. Also, in a physical memory manager where we need to allocate a lot of regions of one block that will be mapped by the virtual memory manager, bitmap allocators tend to work better. Their main drawback is, however, the difficulty of storing metadata about memory, but in all the other aspects, they perform the best in this scenario. Linked list allocators tend to perform very well as coarse allocators that can be used to manage large portions of memory, but terrible when dealing with a lot of small regions. Another important metric when evaluating these algorithms is how prone they are to fragmentation. In my test scenario, I simulated many allocations and deallocations until the memory usage reached approximately 50%, and then I measured the fragmentation a couple of times. I will explain the exact methodology a bit later, but these are the results that I obtained. The bitmap allocator first fit was the best performer with an average of 20% fragmentation. The next couple of algorithms also got a pretty close average at around 25%. The worst fit implementations performed terribly. And the biggest surprise here was that next fit also performs terribly, with an average of 98% fragmentation. What we can learn from this is that while this optimization is great for getting a significant speed improvement, it does this at the cost of making the fragmentation problem a lot worse. Finally, let's look at the wasted memory. We can already see which is the worst performer, the body allocator, which averaged 20% wasted memory. The explanation is very simple. This is caused by the rounding of blocks to a power of 2. Removing the body allocator from the chart allows us to see the wasted memory of the other allocators as well. Here we can see that the bitmap allocator is the most efficient, only wasting around 0.01% of memory. The balanced binary tree and the dual binary tree implementations are next, but these implementations use the map from the standard library, so I will consider these results less trustworthy. The rest of the allocators are the linked list and binary search tree allocators, where I used the element pool implementation. Remember how I said that freeing the pools is left as an exercise to the viewer? By freeing up those pools, we can probably get less memory waste. So, to summarize, which allocator should you use? For the best performance in all aspects, I could recommend some experimentation based on the dual binary tree search allocator, which was the biggest surprise for me. However, if you prefer something simpler to implement, the bitmap allocator first fit is great for managing physical memory. I would not bother with the next fit optimization because even though it has a significant performance improvement, it has the bad habit of making fragmentation a lot worse. If you are implementing a heap allocator, you cannot go wrong with the body allocator. But since it tends to result in a lot of wasted memory, it might not be a bad idea to experiment with some hybrid allocator where you can use the body system to allocate large blocks of memory and some other strategy for making the tiny allocations. In the final chapter of this long video, I will talk about the methodology I used for the benchmarking of these allocators. To get this out of the way, here are some details about the computer I ran these tests on. This is the CPU, memory, and here's the CPU ZInfo if you want more details. I ran the tests on Fedora 37 using this version of GCC, and I also used these compiler flags. I already discussed about the variables that I identified and how I tested against them. So let's look at the implementation of the actual benchmarking code, starting with the speed benchmark. For setup, I initialized the allocator and the random number generators. And after this, I simulate the allocator being used for a while by performing random allocations and free operations for this number of iterations. Alloc random block, as the name suggests, allocates a random number of blocks. The number of blocks is randomly generated in this function, which is where I handle the ratio of one block regions. If the size is not 1, I use this generator that uses the geometric distribution for generating a number between 1 and the maximum size. Back to alloc random block, after allocating the region, I remember it into a vector so that I can free it later. In free random block, I simply pick a random region from the vector of allocated regions and then I free it. Now we get to the part where we actually run the test. Here we repeat this test for a number of iterations. At each iteration, we begin by calling this enforce usage target function, which makes sure that the memory usage is close to the percentage that we want. This is done by randomly freeing or allocating memory until it's close enough to the target. Here the implementation looks identical to the one in alloc random block, except that now we start and stop the clock when calling allocate to measure the time. Finally, we return the total elapsed time. For benchmarking the free function, we have this other run method. Same as with benchmarking allocation, we iterate a number of times, and we first make sure that there is memory to be freed by allocating some random blocks. This implementation looks very similar to free random block, but this time we start and stop the clock when calling free to measure the time. In the main source file, we have this doSpeedBenchmark function, which is used for running the benchmark. This function will run the test a large number of times and will collect all the results. Finally, it calculates the average, the low 95th percentile, the high 95th percentile, and the standard deviation. Now let's see how fragmentation and memory waste are measured. The test is set up pretty similarly. The main difference is in how I run the simulation. This time I increase the likelihood of an allocate operation so that memory usage can grow until we reach 50%. In retrospect, it might have been a good idea to do something similar with the speed benchmarks, but I decided against it because it required rerunning the entire test suite, which took a huge amount of time. The actual testing is done in the run function. Here we run the normal simulation where the probability of allocation or deallocation is 50-50. Every measure iterations, we take a measurement of fragmentation and memory waste. Finally, we return an average of all these measurements. Here's an interesting question. How do we measure fragmentation? For this, I basically devised this formula. The basic idea from which I started was this post from Stack Overflow. Let's look at a simple example where we have 20 blocks of memory, out of which 10 are free and 10 are used. Let's start with a given region size, let's say 3 blocks. To measure the quality of the free space in respect to regions of 3 blocks, we measure how many slots of 3 we can fit inside our free space. In the ideal situation, where all the free blocks are next to each other, we could fit 10 divided by 3, which is 3 slots. But let's say that our memory looks like this. In the present case, we can no longer fit 3 slots, we can only fit 1 slot. So we could say that the quality of the free space in respect to regions of size 3 is 1/3 or 33.3%. Now we want to determine the quality of the free space in regards to any region size. So how could we do that? We could calculate this quality measure for every region size from 1 to 10, and then simply average them out. There's one more thing we need to do to get our fragmentation percentage. The quality goes from 0 being the worst quality to 1 being the best, but fragmentation is the opposite. So fragmentation is equal to 1 minus the average of all the qualities. Something to note here is that this calculation is pretty slow. For the tests where the memory size was 512 megs, these ran for more than 24 hours using the parameters I have set. So yeah, it's pretty slow. Next, I'd like to show you how I measured the memory waste. For this, I started by adding an abstract function to the allocator class, since this implementation is specific to each allocator. For the bitmap allocator, memory waste is basically the size of the allocator structure plus the size of the bitmap rounded to the nearest block size. For the linked list and also the binary search tree implementations, I could simply iterate through the elements of the linked list or the binary tree for entries that were marked as reserved by allocator and then add them up. For the body allocator, we need to count the extra blocks at every allocation and deallocation. This field is used to keep track of the current number of extra blocks. Here is the allocation where I add these extra blocks, and here is the deallocation where I subtract these extra blocks. And of course, I also add the sizes of the actual allocator structure and the bitmap to the total number. Finally, we reach the main file where the fragmentation memory waste benchmarks are executed. This looks very similar to the speed benchmarks, except that here I run them in parallel or multiple cores using std async, since these tests can take a lot of time and we don't need to do any precise measurements of time. And we finally reach the conclusion of this video. If you find any flaws in my testing methodology or in my algorithms, or you find an optimization, please make a pull request. If there are any significant changes, I will make another video with updated benchmarks. The link to the repository containing all the allocators and the benchmarks is in the video description below. I haven't integrated any allocator into the operating system itself that I'm working on, and I will do that in a future video. But I really wanted this video to be a good reference video for all the different allocators, how they work and how to implement them. I really wanted an in-depth coverage of this topic, as most of the materials I found didn't really go into a lot of detail about how to actually implement these algorithms. They just provided a high-level overview. I hope this was useful and interesting, and it was worth the 4 months of work that I've spent on it. If you have any questions, feel free to join my Discord, there's a link in the description. Thank you very much, have a nice day, and see you soon.